There's like my furniture that I want.
Hey, the culinary research circle, I'm part of the. I'm part of the culinary.
All right.
Starting date. And like right to and I'm like, I'm sorry.
Hello, everyone. This time we're going to continue with where we left last time. Last time we have worked on a PERT approximation problem. And now I provided a section that's about Microsoft project. However, we are not going to implement all the procedures. However, I would like to point out that you may find the first section the most useful. If you need to install Microsoft project on your own computer, or if you want to remote access a desktop from a lab like this one. So if you need to use Microsoft project in the future, you can consider using the remote access. I illustrated the steps needed in the last paragraph in section 1. And all the other necessary steps to complete a Microsoft project is also illustrated here. So I encourage you to explore all of them if you need so. Recall that last time we worked on a project scheduling problem. We were given a project schedule table with some duration parameters. A here is the minimum duration, B is the maximum duration, whereas M is the most likely duration. So if you need to do a Microsoft project, one of the necessary input is the duration. Could you tell me which of these three you would want to use as the input for the duration in Microsoft project? Do you think you should use any of these three, A, M, or B, or none of them? Yes, the correct answer is none of them. We want to calculate the expected duration. Recall that last time we also practiced the PERT approximation, so we should instead use the expected duration. However, some of you wondered, since we practiced PERT approximation, right? What's being approximated and how well does this approximation work? So let me illustrate here. I will also show you a simulation example so you can have a sense of the degree of approximation and see how far it deviates. Okay, so first from the PERT approximation, we know that we need three parameters, right? That's A, B, and M. And we also learned that the exact distribution behind it is a beta distribution. So how are these related? Recall that beta distribution, it has two shape parameters. They are called alpha and beta. However, we extended a standard beta distribution from 0 and 1 to a region that's between A and B. So basically, we transfer the left and right limit from 0 to 1 to A and B. But still, there are two parameters we need to find before we can define a beta distribution, right? So how are these two related? It turned out that if we use the PERT approximation, it would mean that alpha is equal to 1 times 4, 1 plus 4 times M minus A, and this is B minus A. And the other shape parameter, that's beta, would be 1 plus 4 times the rest. So B minus M divided by B minus A. Then let's see what the other parameters come in. So using PERT approximation, we know that the mean or expected duration for each activity, right? So this would be MJ or TJ, would be, let's see, 8 minus 4 plus 4M plus B divided by 6, right? And we also have the sigma, which is B minus A divided by 6. So given these, if we need to find the exact formula that looks like the PERT approximation, this would mean that for any alpha plus beta that equals to 6 would satisfy this. So that means if we use PERT approximation, it means the underlying beta distribution has a relationship so that the sum of alpha and beta equals 6. And if we use this formula to derive the standard deviation, we would find that alpha beta would actually equal to would equal to this quantity. So only when alpha and beta are is this number, would this formula be correct or totally exact? For any other combinations for alpha and beta, the PERT approximation would have some error in it. So, and recall, after this, we're also going, last time we also used another procedure that's called the central limit theory, right? To calculate the total duration. So if we want to calculate the sum of all the means, let's just write them as TJ. I think it'll be easier to understand. Well, and we also calculated these quantities. If we have some errors when doing individual activity estimation for duration and the standard deviation, how well does this go? So last time we learned that the central limit theory come into play because we assume all the activities are independent from each other, and the number of activities, that's the count of J or the largest J, is large enough so we can use approximation. But in reality, we often come into projects where there are only a limited number of activities, right? So to complete this project, I counted that there are 16 different activities. It's not much different from 15, and most of us wouldn't consider that as a large number, right? So let's see whether there are any other good methods that allows us to estimate the total duration. Here I show you an example of doing simulation to estimate some unknown quantities, especially when the distribution cannot be assumed. using this central limit theorem, we basically assume that the total duration follows a normal distribution, right? But what if it doesn't? So here, continuing with where I completed last time, we already calculated all the other columns that's in the gray area. That's the expected duration, whether it's on the critical path, and the standard deviation and variance. And using this formula here, I also calculated alpha and beta. These are the parameters for the beta distribution. So using these parameters, we have everything that's necessary to define a beta distribution. Those are in the column of A, B, and alpha and beta. So using these 4 parameters, I was able to generate random numbers for based on a defined beta distribution. I used the formula that's beta inverse, given a random number that's between 0 and 1 and all the 4 parameters. It returns a number that's beta distributed. As you can see, every time when I refresh the sheet, all the random numbers changes because I used a function that's called random to generate random numbers. And every time this function would refresh, and it gives us a different result each time I refresh the sheet. Anyway, as you can see here, for activity B, originally we estimated the expectation to be 10, but the simulated duration this time is 9.69. It's slightly smaller than using the PERT approximation. For activity C and D, recall that last time we encountered this problem where they share the same expected duration, and we had to make a subjective choice between them to use one of them on the when calculating the total duration and the total variance. However, when using the simulation, usually we see that one of them is larger or smaller than the other one. And in this case, I found that activity C has a longer duration than activity D. That's why I would use activity C to be included in the total duration. So using the same idea, I calculated the total duration. As you can see here, the total duration is a sum of some individual durations. And I picked whichever is the longest one when we have a branching structure. So instead of subjectively choosing one of the equal duration when we have a branching structure, this time we were able to pick the largest one where I used the max function. All right. So in this simulation, I found that the total duration was 84.24 instead of the 89.17 using the PERT approximation. As you can see, they are somewhat similar, but there's still some difference between them. So this is how you can generate one round of a simulation. You supply the parameters, that's A, B, alpha, and beta for a beta distribution. Then we use a rand function to generate a random number. And given that, the beta inverse function would return a beta distributed duration. All right, any question at this moment? Great. Now let's see how we can use the randomly generated beta distributed durations to give us a variance estimate. One round of the simulation, as you saw just now, give us an estimate for the total duration. But how can we derive the variance? This can be done if we generate multiple cases or a larger sample size for the simulated sample. For example, if we run 7 times of the simulation, this is how I got. This is what I got. This time I transposed the sheet so that on each column we see the activities. There are in total 16 activities. And if I generate the duration for each of them, you see that I was able to find the total duration for each of the 7 cases. And out of that, I can calculate a mean using the average function and also the variance and the standard deviation. So this time I was able to get the standard deviation and the variance if I generate multiple cases. So any questions? How you can use simulated sample to calculate mean and standard deviation? Hi, what's up? No, that's a good question. So apparently you have already questioned that you don't think a sample size of 7 is stable or large enough. That's very sound reasoning. So let's see what happens if we enlarge the sample size. So here, following that, I created a small, slightly larger sample, but it's still considered a small sample in 100 cases of the simulation. And for each of them, I used the beta distribution to generate the duration of individual activities. Then I used the same formula to count the longest path along these activities. So for each case, I generated the total duration. And let's see how they compare with our Perl approximation. So here, out of the 100 cases, the average is 89.89, which is somewhat close to the Perl approximated mean. However, you find that the variance and the standard deviation are somewhat different. So how different are they? If we go back to the approximated quantities, we find that between the simulated sample and the approximated quantities, the mean only differs by 0.8%. So they're not quite different in terms of the mean, but let's see that the variance will differ by 26.6%. So it's a large difference. And some other simulations would also find that the variance could differ by almost 50%. So if we use Perl approximation, the variance is somewhat questionable. Then because of that, the standard deviation could differ by almost 15%. Okay, if the variance is somewhat questionable, how can we still derive any uncertainty or probabilities if we cannot use the central limit theorem to depend on the normal distribution? So this turned out to be not so complicated. For most of you, I consider that this might be much easier to understand than if we use a normal distribution to derive probability. So using a simulation, where I created 100 cases, the way to calculate probability is just a ratio or fraction. To calculate a probability that the activity can be completed within 85 days. This is done by dividing the number of cases out of 100 that has a total duration that's smaller than 85 by the total number of cases, which is 100 in this case, right? Because I created a sample size of 100. So this is the result I got. So out of the 100 cases, I found that 11 of them had a duration that's smaller than 85. So here I use the count if function. Similarly, I counted that 78 of them had a duration that's between 85 and 95 days, and 11 of them had a duration that's longer than 95. So that's how you can calculate a probability out of a simulated sample. You just count and divide. Any question here? All right. So using the same idea, I was able to calculate some accounting or financial indicators using the same idea as before. Just here that I substituted the simulated probability for the herd approximated and the normal distributed probability. So as you can see, doing a simulation is not complicated, and in many cases, it gives us a much better result than if we depend on some approximated distribution. And in reality, if we actually run a simulation, we would normally use a very large sample size, like 20,000. That's the regular threshold. So imagine that I increase the sample size to create many rows. So they take 20,000 rows. Then that's how I can have a very accurate estimate or out of a simulated sample. The reason for creating so many cases is that if we use the simulated quantities here, there are two sources of errors that comes into play. First is because of the sample size. Because I simulated each of the case using a random number, right? So each of the random number has a sampling error, which goes here. The sampling error will be smaller and smaller if we increase the sample size. So that's why we want to increase the sample size. However, there are other error sources like here. I generated all the random numbers out of these supplied parameters that's in alpha, beta, A, and B. There might be errors when we supply these parameters. They may not accurate. So this is another source of errors. So if you want to create the best simulation, you want to control two sources of errors. First is whichever parameters you supply to it. You want the most accurate parameters you really estimated from other models. There's a second source, that's sampling error. You want to create as many cases as possible, so you control the sampling error. All right, this is a demonstration of using simulation to estimate some unknown quantities. Any questions? All right, now let's move on to the next step, which is engineering accounting. Please go to our shared lab notes where you can find some useful formula. And we also need to start working on interest rate problem. In example 1, there are 4 problems supplied where you need to calculate some effective rates of interest. Then there's another problem on present value and annuity. There's another set of problems on future value and annuity. So please start working in groups of 2 from example 1. And let me know if you have any questions. So one question for you, since we have discussed the accounting section in the lecture, were we introduced about any Excel functions to calculate any of these quantities in annuity? Oh, okay, I see. The good news is that we don't really need Excel to calculate any quantity for any of these questions, as long as you know some basic formula, like how we can find the sum of a geometric progression. So my takeaway for this economic accounting section is that if there's any formula that you want to take in your note in an open book exam, it'll be this one. You really don't need anything else, actually. So using this one, you can actually solve any all of these questions following. All right, we have 10 minutes where you work on it. Then I'm going to start illustrating from example 1. So raise your hand if you have any questions.
Yeah, the first one, the second question.
So the first question is asking us, is the 24%, I think for the water, is for the nominal rate or? They're given two cases, is it the nominal or effective if one, the interest rate compounds monthly, and two, if it compounds yearly. So my understanding in both cases, the 24 is nominal.
Calculated annually. Oh, it's 1 + 5. Has any of you started working on example 2? Yeah. That's not fair. One plus five.
Down payment, just minus it's from 1,000. They're down. Then what if they address? But they always. So, saying, we're crazy. The present value is 800. And then what would I ask them? That has to be.
All right, which team has completed example 2? Any teams on example 2? Okay. All right, let's start working on them together from example 1. In the top part of the shared lab notes, you find that there are additional equations and materials. So I would point out that I explored 5 Excel functions about annuity. To complete any of the homework questions, I really don't think you need any of them. You can simply use a calculator and some other simple functions to calculate instead of depending on these functions where you may not sure how these functions work. In example 1, we are given an annual interest rate of 24%. If the interest compounds monthly or daily, this 24% annual interest is a nominal term. So the question to the first part is that no matter whether it compounds monthly or daily, which is a more frequent assessment than an annual interest, right? Then it means this annual 24% is a nominal term. However, if I say that the interest is accounted every year, that would mean that here the nominal rate, that's 24%, coincides with the effective rate, that's also 24% per year. Then let's see what it means by compounding monthly and daily. If we compound monthly, it will mean that the this rate is the annual rate divided by 12. So it'll be 24% divided by 12, right? That's 2%. Then the effective annual rate. So we call this effective monthly rate. Then we transfer that to the annual term again. That would mean that if I have $1, I put in the well, if I borrowed $1 from the bank in my credit card, right? After it would give me an interest every month for 1 plus 2%. So if I borrow it $1 now in a credit card, after 1 month, it becomes $1.02. And if I continue it to another month, then after 2 months, it'll be 1 plus 2% squared, right? Then after 12 months, it becomes this quantity. So I raise this 1 plus 2% to the power of 12. That's how you can calculate a effective annual rate. I saw a confusing face. Are you clear with what I'm doing here? Any questions? Okay. All right. So this basically says that for every month, there's 2% of interest. And the interest would compound, so it accumulates. Whatever interest derived from next month would become part of the principal for the next month. That's what it is. So if I want to calculate the total amount, I would have to use a power. For daily, it's the same case. It'll be just that we need to divide the annual by the number of days in a year. It'll be 365, and this quantity is somewhere around 0.06 and so as you can see, the daily interest rate seems very small. That's the effective daily rate. We derive effective rate from the nominal rate divided by the number of months or days in a year. Now let's see what it means in annual. So if I borrow $1 within 1 day, it becomes 1 plus this 24% divided by 365, right? After 2 days, I raise it to the power of 2. After 3 days, it'll be power of 3. So after 365 days, that's 1 year ahead of time. That's how I calculate the total amount after 1 year. And this quantity will be 1 point, let's see. 1.27. And that means if I divide minus 1 from this quantity, that's the part of the interest, right? Because the principal is 1. So if I use 1.27 to minus 1, that's the interest rate, basically. All right. I also gave another question that's on if the bank wants, well, let's see. Okay, if the interest compounds daily, how can we find the effective monthly rate? This is not using the same idea. We can easily find that. We simply use this. Because it's still compounding daily, but we want to find a monthly interest, effective monthly interest rate, right? So the interest part is the same. We still divide the 24% by 365. So this quantity is the effective daily rate. But to find the effective monthly rate, we would raise this quantity to the power of 30. Then we minus 1. So the remainder is the interest part. And this quantity is 1.99%. So any question in part 3? All right. There's one remaining question. If the bank wants to profit at the same effective annual rate as in part 2, so here this quantity will be 1.26. Well, it's almost 27, but let's make it more accurate. So that means here the effective annual rate is 26% plus 0.82%, right? So this is the interest rate for profit for 1 year for the bank if the interest compounds monthly. And this quantity is 27% and 0.11. Okay. So as you can see, the trend here is that if it compounds more frequently, the effective annual rate is higher. Do you see that? If out of the 24% nominal annual rate, if the interest actually compounds monthly, the effective annual rate is 26.82%. If it compounds daily, so it's more frequent, the effective annual rate would become 27.11%. So as you can see, if it compounds more frequently, the effective annual rate is higher and higher. However, this quantity has a limit. That's why I created section 4, the part 4 question. So in 4, it asks if it compounds continuously. So the frequency is infinite. It means the assessment of interest is infinitesimal. So it can be as small as you can imagine. Then to find this quantity, we basically do this. We use 24% and divided by a quantity and raised by the power of the same quantity. And we need to find the limit as this n goes higher and higher. So that's where you can find the limit to be useful. I need to find the limit when n goes to infinity, how this quantity changes. So it turned out to be that this quantity has something to do with an exponential function. So I need to use exponential function and give it a 24%. And you find that this quantity is 1.27. And after that, it's 1, 2. So as you can see, if we compound daily, this is already pretty large number. That's 365, right? It's very close to the limit. That's just slightly larger than if we compound daily. Then to find the effective interest rate that to equalize these two quantities, we would just need to solve a function. So here we need to change this interest rate to be equal. So in part 3, the last section, in part 3, we would have to derive a function, an equation, so that if we plus 1 and let's see, 2%, right? And raised to the power of 12 minus 1. This is the interest rate, effective annual interest rate if we compound monthly. So this is that we need to equalize this part to an unknown quantity. So this is the effective daily rate raised by the power of 365 minus 1. So we need to equalize this function. Then solve it, gives us an effective daily rate. Well, yeah, let's just use it in percentage. This would be somewhat slightly smaller than what it was. As you can see here, it's 0.066%, and the quantity that would equalize the effective annual rate between the monthly compounding and daily compounding would be this. So basically, to solve any of the economic accounting problems, we need to remember some equations. Next time, we are going to find the summation equation for an geometric progression to be the most useful. And sometimes we need to solve some equations like this one. Then we can find the unknown quantities. All right, this is the end of our discussion. Please submit your worksheet with your names on it. Thank you.